Exercise 2H is pretty straightforward, and I say this every lesson I know, but this one is just an application of what we know as simultaneous and linear equations. Now, we also want to look at the geometry of simultaneous linear equations because that's essentially what we're looking for when we have simultaneous linear equations. If I give you two equations and I tell you to solve for x and y, geometrically, what does that tell me? If I've got, let's say, this line and that line there, and I tell you to solve for x and y, I'm telling, let's say this line, blue line here, apologies, and this purple line, there we go. And I say find the solve for x and y, where the blue line and the purple line equal. I am essentially telling you to find that intersect. That is exactly what I'm looking for. So where x equals a certain value and y equals certain values, that's the coordinate of the point of intersection. Make sense? Lovely. Now, that's what happens when we have one unique solution. We have the lines passing through at one point. Now, assuming we don't have any restrictions in terms of how far across it goes or whatever it is, every single line that is different and not parallel will have a meeting point. Even if they're like this far apart and they're only slightly not parallel, that will meet at some stage. That makes sense, yes? Awesome. So that's why we have one unique solution. If there are no solutions, and I say you're trying to solve for x and y using simultaneous equations, and there are no solutions, what possible outcome could there be if there are no solutions for two lines, no intersections? Yeah. Perfect. Oh, sorry, say that again. So that's a different one. So I'm focusing on no solutions. Perfect. The two lines are perfectly parallel. So if I draw a box there, and I use my blue line like this, and my purple line I draw like this, right now, obviously, they're not parallel. But assuming they are parallel, those lines would never meet, and therefore, you would get no solutions. And that's one solution. An infinite number of solutions. What does that mean geometrically? If I have an infinite number of solutions, that means the two lines are the same. Does that make sense? So for example, and I know I'm drawing this really shoddily, I do apologize. If I have my blue line here, and I have my purple line here, does it make sense for me to say that that is a point of intersection? Yeah? That's also a point of intersection. That's also a point of, every single point on this line, an infinite number of them, are points of intersection, and therefore gives me an infinite number of solutions. Okay? Any questions? No? Okay. Now, algebraically, what does that mean? So we show that, in this question, show that 2x plus 3y equals 6, and 4x plus 6y equals 24 have no solutions. Now, I've just gone ahead and had the liberty of drawing boxes around the equations, just because I know it's a bit harder to see when I type it out. So I've got 2x plus 3y equals 6, and 4x plus 6y equals 24. We have to show that there are no solutions. So if we looked at a geometry of simultaneous equations over here, what situation gives us no solutions again? They're parallel lines. Let's go ahead and make them into the gradient intercept form that we know of y equals mx plus c. So I'm going to get this equation over here. So instead of 2x plus 3y equals 6, I'm going to write 3y equals to negative 2x plus 6. All I've done is I've taken away 2x on both sides. I'm going to divide both sides by 3, and I get y equals to negative 2 over 3. X plus 2. Are we okay with that? Are we okay with that? Yeah. Awesome. So now I'm going to do the same thing with the other equation. I'm going to say 6y equals to negative 4x plus 24. From there, I'm going to divide both sides by 6. So y equals to, what's the simplified version of 4 over 6? Negative 2 over 3, lovely. X, and then 24 divided by 6 gives me 4. All right, what do you notice?
Same gradient.
Same gradient, perfect. They're same gradient. But what's telling me that they're not exactly the same line? How come there are no solutions and not an infinite number, Ryan?
Different y-intercepts.
Perfect, different y-intercepts, right? This plus 2 and plus 4 value tells me how high up on that y-axis it's going to be. So in this case, I've got two lines with different y-intercepts, same gradient, and therefore have no solutions. That's one way you can do it. Another way you can do it is to solve it simultaneously, as in legitimately using the simultaneous equation algorithm. Let's give that a go. So let's say I have 2x plus 3y equals to 6, and I've got 4x plus 6y equals to 24. So all I've done is I've just written one on top of the other. Can anyone tell me what would they do? Substitution or elimination? Substitution or elimination? Am I speaking too quickly? Elimination, let's do elimination. I'm going to multiply this one by 2, and I get 4x plus 6y equals to 12. Can you already see an issue? Yeah, I've got 2 equations. Let's focus on this part over here. I've got 4x plus 6y twice, but they equal different things. If you could already stop there, you already know that's not true. But if you wanted to continue, you would eventually get, and let's assume that we just replace that and write that there, whatever it is, and we get 24 equals to 12. You won't actually get, if you're solving this, you won't actually get something tell you no solutions. You just end up with a value that just makes no sense. 24 does not equal 12, obviously, and therefore it has no solutions. Does that make sense? Yeah? Algebraically, that's what you're going to end up with. All right, let's do the last question over here. The lines m take away 2, x plus y equals 2, and mx plus 2y equals k intersect at 2,8. Remember, what does the intersection tell me? Perfect. It tells me where they meet. In this case, it's where x and y will be. So now I'm looking at finding the values of m and k. I've got my 2 equations. I'm going to substitute those values in. Now the question is, which equation do I substitute these points in? This point in. Why do I substitute a point in? I feel like I need to pause the video and let you guys think about that for a second. Yes. Yeah, find the unknown, exactly right. But how come I'm substituting this point in? Well, it's because this point 2,8 we know lies on the line. So whatever variable or whatever unknown I end up with, I know is correct relative to the line itself. In this case, which equation passes through this point 2,8? Both of them, perfect, because it's an intersection. And therefore, I'm going to substitute into both of them. So I'm going to write this one over here in green. I'm going to write bracket m take away 2. Instead of writing x, I write times 2. Plus y is 8 equals to 2. And then this one over here, I'm going to write as m2 plus 2 times 8 equals to k. I'm going to simplify the green one. I know it's getting really messy, apologies. I get 2m take away 4 plus 8 equals to 2. Therefore, 2m equals 2. So that's 4 on the left-hand side. I'm going to take away 4 on both sides. Negative 2. Are we okay with that? Yeah? And therefore, m equals to negative 1. All good? Lovely. We found one of our answers. But we also need to find k as well. So now I'm going to substitute it. Let's simplify this equation in the blue first. 2m plus 16 equals to k. I'm going to go ahead and substitute that value in. And I end up with negative 2 plus 16 equals to k, which means that the answer for k is 14. So m equals to negative 1, k equals to 14. So with an understanding of geometrically what simultaneous equations are, we can actually solve these questions. The only other thing I do want to talk about is stuff that you guys have already done in the past. So I'm going to use this box again to represent my Cartesian plane, with this being 0. If I have 2 lines, and they're represented by, let's say these lines represent the cost of hiring a bike or whatever it is, right? You guys have all seen those questions. So what I'm trying to look for is, well, there we go. What does that intersection tell me? It tells me that at that point, let's say that this is the number of hours, right? Number of hours you've hired a bike. Let's say 4 hours. At 4 hours, it costs the same. And the question might be, well, at a certain number of hours, how much would it cost? Or at whatever hour it is, sorry, I should say, how much time does it take for both companies to cost the same, right? So the idea is, can we find the intersection in terms of finding the point by using simultaneous equations? And then can we use that in order to solve the problem? Do I have any questions? No? Okay, so if you've taken down these notes already, exercise 2H, the lesson plan has the questions over here, exercise 2H. If you've finished that already, please feel free to begin on chapter 2 review. Otherwise, let's begin.